2.5 years ago, I fixed my Prius's high voltage hybrid battery, and guess what? Yeah, it's back. P0A80. That's the code telling me that the hybrid battery is bad. I can't say I was excited for this when I first found out.
Oh man, oh no.
But it ended up being a fun project in the end with some design work involved in fixing it. Not that it was necessary, I just got a little bit carried away. Anyway, you'll see later in the video. And just to clarify, I'll be calling these modules and not cells throughout the video. A lot of people call them cells, but they're actually modules. There are 6 1.2 volt cells connected in series in each of these modules. And please, these batteries have deadly voltages, so fix your car at your own risk. Last time I fixed my battery, it was a lot of work, like a ridiculous amount of work. I think it took at least 2 to 3 weeks. So this time, I want to see if there's a quick shortcut to fixing the battery. Alright, let's get into it. So first, let's measure the voltage on each module. But before that, let me remove the bus bars from one side of the pack. There we go. Now the voltages are safe to work with. If I can find any modules with significantly lower voltage than the others, then I can just buy replacement modules and swap them out. I'm looking for anything that's more than 0.5 volts lower than the others. And after measuring all 28 modules, they are all within 0.3 volts of each other, which means there are no obviously bad modules here. So unfortunately, I guess it won't be that easy. So next, I'll do a load test on each module to find the weakest ones. For a load test, I'll need a car's headlight light bulb, a multimeter measuring DC voltage, some Alligator clips, and a stopwatch. So I'm going to connect everything like shown in the diagram. Notice that I did not connect the other end of the light bulb yet. Before I connect it, I'm going to write down the voltage of the module. So now that I got the initial voltage, I'll connect the other end of the light bulb, and at the same time I'll start my stopwatch. After 10 minutes, just before I disconnect the load, I'll write down the voltage that the module finished at. I'll repeat this for every module in the pack, and that will give me an idea of which modules are weak. So here's my setup. There's the light bulb, here's my multimeter, and I'm using my phone's stopwatch. And it looks to me like the quickest and easiest way to do this is to leave the pack in the car and test each module in there. Why do the extra work removing the pack from the car to bring it indoors? Oh, I guess that can happen. Well, after the rain went away, I just kept testing and testing and testing, well into the night. And wow, to my surprise, I only found one module that performed much worse than the others. So I bought a replacement and I'm gonna test it before adding it to the pack, just to make sure that it's good too. And it's good. Okay, let's swap it out. Again, to save time, I'm just going to flip the battery pack over while lifting it up and land it on the back seats to unscrew the modules. No use removing it from the car, right?
Maybe I should have taken it out of the car.
I guess I'll just go to sleep and finish tomorrow. Alright, so there are plenty of videos out there on how to disassemble the pack, so I'm not going to get into the details. Instead, I'll show you a quick montage. After removing all the modules from the pack, I lined them all up with all the positive terminals on one side and all the negative terminals on the other side. And I swapped out the bad module with the replacement. Now I'm going to balance their voltages by connecting them all in parallel for a day or so. Alright, so it's been about a day, and now that the voltages are all balanced, I'm ready to assemble it again. Okay, so after all that, the pack is back in the car and I'm ready to take it for a test drive.
I gotta test my Prius more often. At 11:39 p.m.
So I'm on my way home from the test drive and it seems to be okay, but my gut feeling tells me otherwise, so I'm a bit skeptical. Let's see how it does during my work week. And here we are the next day. Okay, I know I said I was taking a minimalistic approach this time, but these MPG bars are just laughable. Also, you can't see it here, but the overall MPG dropped way lower after a bit more driving. And the engine is revving really loud while I'm driving, and it's almost always on, even when I'm stopped at a red light. So it probably won't take long for the error code to pop back up, so I'm going to continue fixing the pack. Well, I'm pretty sure that some of you were probably yelling at me when you saw how corroded my bus bars are. So I'm here to tell you that I don't think it's going to make a difference if I clean them or not. I think it would be bad if the bus bars were rusty in the middle here, because this is where they make electrical contact with the battery, but they're mostly okay there. And to see if I'm right or wrong, I'm going to run an experiment. A bus bar is just a piece of copper that conducts electricity just like a copper wire. Ideally, a conductor would have no resistance, meaning that it would deliver all the electric power from the source, which is the battery, to the load, which is the motor. But in the real world, conductors always have some resistance, it's just very little. And where there is resistance, there's a loss of power through that resistance. Also, the greater the resistance, the more power will be lost through the resistance. So you probably know where I'm going with this. Corrosion, or rust, adds to the resistance of the bus bars. So if this extra resistance is significant, the bus bars will lose a significant amount of power while the battery is supplying the motor with power. And what's cool is that this can be measured. You see, at the left side of the bus bar, there's the voltage, which in this example is the voltage of the battery. Let's just say it's 10 volts. And when current is flowing, then there will be a lower voltage on the right side of the bus bar. Let's say 9.5 volts. The difference in these voltages is called the voltage drop. And with a multimeter, I could just put my probes across it and measure the voltage drop directly. If I know this voltage drop, and I know the current, let's say 10 amps, I can calculate the power lost in the bus bar. This is the voltage drop multiplied by the current. So in this example, I lost 5 watts of power. How would I know if this is a significant amount? Well, in this specific example, the voltage of the battery is 10 volts, and it's pushing 10 amps of current, so it's sending 100 watts of power. And we mentioned 5 watts is lost in the process, so the motor received the rest, which is 95 watts of power. That's a 5% loss. That's kinda significant. But let's see what these numbers actually are with the Prius instead of the numbers I just made up for this example. I have a feeling it's going to be way less than 5%. Alright, so I connected my multimeter to one of the bus bars to measure the voltage drop while I'm driving. And for measuring the current, I connected this clamp-on current meter to the output of the pack. Please, please, please don't do this at home. It's extremely dangerous. So, I went out driving and taking measurements for way longer than I care to admit, because I measured the voltage drops on all of the bus bars, one by one. And you know, I was out testing my Prius again. So it looks like they were all around 2 millivolts, and sometimes they go as high as 6 millivolts for a split second. But hang on, what's this bus bar doing? Whoa, 110? That's awful compared to the rest. And the highest current I saw was 125 amps, which is quite a lot. Alright, well, we got enough information to do the math now. So there are a total of 26 bus bars. One of them had a voltage drop of 110 millivolts, and the rest only had 6 millivolts each. And I'm just gonna convert the millivolts to volts here. and the current was 125 amps. The power loss through that one bus bar is 13.75 watts, and the power loss through each of the 25 bus bars is 0.75 watts. Now there are 25 of these, so the total power loss through the 25 bus bars is 18.75 watts. So add the two up, and the total power loss through all of the bus bars combined is 32.5 watts. How much power is the battery trying to deliver to the motor? Well, the entire pack is about 200 volts and the current was 125 amps, so 25,000 watts. Whoa. So we're only losing 0.13% of the power through the bus bars. So you won't be getting much more performance by cleaning them. However, I can't say the same if your bus bars are much rustier than mine. Okay, so just to double down on this, I'm going to clean the bus bars and then remeasure them. Don't do this. This took a painfully long time. If you're gonna clean them, then do yourself a favor and just buy a replacement set from eBay. But make sure you get the ones that come with smooth surface nuts rather than the rough ones. Okay, so here's what they look like before I cleaned them. And here's what they look like now. So they're pretty much the same as they were before I cleaned them. Maybe they're a little bit better. But none of them go super high to 110 millivolts anymore, so that's good. And yes, I measured all of them again. So let me bring up an important point that I did not mention earlier. The extra power dissipation due to rust on the bus bars generates more heat on the bus bars. And batteries hate extra heat because it lowers their lifespan. So I did not measure how much they heat up before and after cleaning them, so I don't know if it's substantial or not. It's your call. If you want a peace of mind, then you can clean them. I mean, replace them with a new set. So the pack is obviously still bad. 36 mpg, but it's dropping like a rock. It'll probably go way lower after some more driving, and the engine is still revving really loud while I'm driving. Looks like there's no way around it. The car has to be fixed a long way. I didn't want to have to do this, but let's buy some charge cyclers and charge cycle the modules. And this time I'm going to remove the pack from the car and bring it indoors. So you might be wondering what charge cycling is. Well, it's essentially charging and discharging the modules multiple times. In order for you to understand why we need to do this, I need to tell you what happens with older batteries. These modules, when they are brand new, are rated for a capacity of 6,500 mAh. This is the maximum amount of energy that they can store. And used batteries will lose maximum capacity over time, and bad ones will not be able to hold much energy at all anymore. So most people say that charge cycling modules restores their capacity because it fixes a problem called the memory effect. This happens when a battery does not get fully charged and does not get fully discharged for many cycles. And this causes crystals to form inside it, and these crystals inhibit the flow of electricity, so the battery ends up remembering this smaller capacity. And a lot of people, including myself in my previous videos, blame the memory effect for the modules losing capacity. But it turns out that the memory effect was a huge problem with NiCad battery technology, and that's one of the reasons why NiMH batteries were invented, which is what the Prius uses. It even shows right there in the Battery University website that I showed last time. NiMH is less prone to the memory effect. So while NiMH batteries still have the memory effect happen to them, it is very minimal and negligible. Then how come the capacities of used modules are still lower than new ones? There are a few reasons, but the main one is this. Remember the corrosion and the greenish bluish powdery stuff on the bus bars? That's electrolyte leakage, which is a hydroxide. So you're losing the chemical contents from the inside of the battery over time, and charge cycling is not going to help with that. Then what's the point of charge cycling them? Well, it's for measurement purposes. We're going to be measuring their capacities and we'll rule out the modules with low capacities. For me personally, I want all my modules to have at least 5000 milliamp hours. So I'll be getting rid of the modules lower than that and buying replacements. Last time I fixed my car, I used C240 duos for charge cycling my modules, and if you've seen the videos, you know that these did not work well. They were very inaccurate. So I recommended maybe getting the EV Peak CQ3, and that's what I'm going to use this time. I bought 2 of them to be able to charge cycle 8 modules at the same time to get this done quicker. And in case you're wondering, this B Quad CQ3 is the same thing as the EV Peak CQ3. Alright, let's set them up. For those of you who are interested, here are the settings for the CQ3. This video is already way too long, so I'm not going to get into the details here. Instead, I uploaded a video on my second channel. If you want to check it out, the link is in the description. But I do want to draw your attention to the capacity cutoff setting and explain what it does. So while the charger is charging the module's voltage keeps increasing. Pretty straightforward. But at some point, that voltage will actually slightly drop. This is the point where the module is fully charged, and this is exactly what the charger is looking for. Once it sees this slight voltage drop, it knows it's done charging. But if it cannot detect it, then the capacity cutoff will be a failsafe so that the module does not get overcharged. So in this case, if it reaches 6500 milliamp hours, it will stop charging. Oh, and if you're going to cycle your batteries, make sure that your pack is not near an air conditioning vent. The AC vent blowing on it periodically will mess up your cycling results. The voltages of the batteries change with the changing temperature, so your AC can trick the charger into thinking that it's done charging the module when it's not. Okay, so why did we set the capacity cutoff to 6500 milliamp hours? Actually, in my previous videos, I was setting it to 7500 milliamp hours, but in retrospect, this doesn't make sense, and I'm not sure why others are doing it either. If they're rated for 6500 milliamp hours, why are we setting it to 7500 milliamp hours? They can get damaged from being overcharged. Plus, they can't even retain most of the energy given to them past 6500 milliamp hours. What do I mean by that? Well, when you finish cycling a module, the charger will show 2 milliamp hour capacities. One for when it was charged, this is what you put into it, and one for when it was discharged. This is what you got out of it. Notice that the charge is larger than the discharge. In a perfect world, they should be equal, but in reality, some energy is wasted during charging. And if you try charging past 6500 milliamp hours, basically all the energy you're trying to put into it at this point is wasted. You're not going to get any more discharge capacity out of the battery by charging it to 7500 milliamp hours. And I tested this hypothesis on a number of modules just to confirm this. And by the way, most of the extra 1000 milliamp hours just turns into heat and internal pressure, which creates swelling and can damage the battery and lower its lifespan. So anyways, when we're cycling the modules, the discharge milliamp hour is what we care about. That's the measured capacity of the module. And the reason we're cycling them multiple times is to aim for consistency so that we can be confident in the measurements. And most people create a table or a spreadsheet to keep track of their cycling results, and that's what I did too. I know spreadsheets are boring, but don't skip this section because I have some really important points to make. But first, let me explain what you're seeing here. So the rows have the module numbers, and the columns have the charges in green, and the discharges in blue. And the number of cycles I did is definitely overkill. This is because I ran a lot of extra experiments, like the capacity cutoff setting we just talked about. Now I want you to pay close attention. The first discharge number is irrelevant. Let me repeat. The first discharge number is irrelevant. This is because the modules are not fully charged when you remove them from the car. They might be charged to 70%, 50%, 30%. It could be just about anything, but they're definitely not going to be fully charged. Don't make the mistake of thinking that you gained a bunch of capacity after the first 2 cycles. I've seen plenty of people make this mistake. As much as I would love it, this module did not go from 2643 to 5725 after 1 charge cycle. Alright, so I placed an order for my replacement modules now. Toyota does not sell them individually, they only sell the entire pack. so you gotta buy them used. And once you get them, it's a good idea to cycle those too to make sure that they're good. So while those are being shipped, let me show you something. While I was cycling my modules, I found that the better the module is, the smaller the voltage drop is when it's fully charged, and the harder it is for the charger to detect it. And it turns out that they can't detect the full charge on almost all of my good modules. But after running a lot of tests, I realized that this is not a bad thing as long as your discharge capacities are consistent. That being said, I have a different problem with this capacity cutoff thing. When it hits the capacity cutoff, it will stop the cycling process even if you set it to cycle multiple times. And then you gotta manually start a new cycle. And I have a full-time job, so I only have the mornings before work and nights after work to program these to start cycling. So oftentimes when I wake up in the morning or when I come home from work, most of these channels hit the capacity cutoff hours ago. So they were just sitting here for hours doing nothing. I really wish I could have someone or something press the escape button, write down the capacities for me, and then start a new cycle. Hey, honey?
No.
Alright. But there's gotta be a way to automate this. This would speed up the process so much and then I wouldn't have to constantly keep looking at this thing. And wow, I just had a friend tell me that her Prius's battery died too. What are the chances of that happening right now? Alright, let's fix her battery too. So I threw a calculator together real quick to see how long it's gonna take me to finish cycling my pack and to cycle hers. And holy moly, it's gonna take like 3 weeks. So instead of spending 3 weeks cycling them manually, let's spend a few months designing something that'll do it automatically for me. My plan is to hack into the charger, connect a microcontroller to it, and then connect a mini computer to the microcontroller. The microcontroller will be my translator between the charger and the mini computer, and the mini computer will do the heavy computing. It will decide what buttons to press and when to press them. And it's going to log all the data and do the spreadsheet for me. Alright, let's grab a CQ3 and take it apart. I'm gonna modify this LCD so I can look at its signals. Alright, time to spy on the signals. What are these signals, man? This is not what I expected. This is gonna be harder than I thought. So my goal is to read this screen with the microcontroller. So I wrote some code and it's not working.
What is that?
By the way, it's reading the LCD multiple times per second. That's why you're seeing it constantly moving up like that. But the weird characters we're seeing here are definitely not normal.
Well, there's a 3 in there.
So I might be onto something. So I spent a few more hours writing some code and
What in the world? I mean, sometimes it's reading the right thing.
So I spent a few more hours coding.
Okay, almost there.
So I spent a few more hours coding.
Yes. Look at that. Finally.
So now that it can read the LCD, let's figure out how we can send button presses to control the CQ3. Up to this point, I've just been pressing it like this with the button pad connected to the CQ3. I'm pretty sure if I just short the pins here, we should get a button press. Yep. Well, that shouldn't be too hard to code. I wish everything was this easy to figure out. Alright, up to this point, I've only been controlling one channel on the CQ3. So now let's make it control multiple channels, which requires more circuitry, and yeah, more code. I'm also going to connect the mini computer, which is called the Raspberry Pi, and we'll be talking to the microcontroller with it through this USB cable that I connected between them. So, as a proof of concept, let's try it out. Let's try typing left. So left, and let's hit enter. There we go. We went left with this channel right here. So let's type left again. Enter. Here it is. So let's try right. Let's type right. Right. And press enter. And now we change screens to the right. Or I should say we press the right button on that channel. Okay, let's change screens. Change screen. Hit enter. Change screens. Okay. So now we should be controlling this one right here. Let's type right. Let's type right again. And oh, beautiful. Did you see that? Through this spaghetti of wires. Well, I thought what I had earlier was a huge mess. Look at this crazy thing. I don't even know how this thing is still functioning properly. I got stuff floating around everywhere. And this is only for 2 channels. Imagine 4. So this is just getting way too out of hand. And this is exactly the reason printed circuit boards were invented. So I'm gonna design a circuit board from scratch and order that, and this will look so much nicer. And this is where PCBWay comes in, the sponsor of this video. Let me prepare my desk while I tell you about them. PCBWay is really fast at producing prototype PCBs, and their prices are really competitive. I've ordered my PCBs from them many times before, and they have never disappointed. I'm always amazed at their build quality and speed. Thank you PCBWay for sponsoring this video, and a huge thank you for your patience. I'm not going to tell you guys how long they've been waiting for me to finish this video for, but it was long, man. Thanks again, PCBWay. So back to my boards that I designed. These are just bare circuit boards. I still have to solder the components on them to make it work. I designed the board so that I could mount it directly on the CQ3. And the Raspberry Pi is going to get plugged in right here later. Let's also get a nice little enclosure for this Raspberry Pi. Well, this is only half the job. I've still got to code the Raspberry Pi to automate the whole cycling process. So I got 2 modules as my guinea pigs as I designed the code, and I don't need the LCDs anymore since I can see everything on the computer now. And I'll spare you the details and the headache of coding it. So after a few days, I'm pretty much done with the code. But I got a cool idea. I'm going to make the program send me a notification on my phone when it's done cycling a module. This way I'll know when to swap out to the next module without having to check the Raspberry Pi. Alright, let's take it for a test run. Let's go ahead and start it. Hit enter. It's going to create some files for me to keep track of the charges and discharges. And there you go. So it's doing its thing. It's setting it up for cycling now.
And now it's gonna start. There you go.
So I know this looks like a mess, but don't worry about it. All that matters is that it works. I could have made it more user-friendly, but I'm the only one using it, so you know what? It's fine. Right now I'm just running it on the 2 guinea pig modules. They're only charging to 100 milliamp hours and a 1-minute delay, so I'll come back in a few minutes when they're done.
Okay, here we go. After a short time it finished, it got to the 100 milliamp hours. And I pressed escape to exit. And actually records those numbers. And I'm going to be getting a notification in about 15 seconds from now. Okay, 2 seconds, 0, here we go. Oh, what is that? Oh man. Okay, what's the problem this time? What's the issue now?
Okay, I found the issue. The sample code that I found for sending notifications used dev over here. And I remember I didn't like dev, so I changed it to device throughout my code. But I forgot to change this right here.
And let's run it again. Okay, here we go. Here comes the countdown. Okay, 3, 2, 1, and nothing. Oh, wait. There it is, okay. And the next one. Oh, that one's not done. I had 3 cycles set for that one. It just started the next one. But this is gonna be great.
And you know what? Let's also make real-time graphs of the charge and discharge curves while we're at it. Alright, finally we are ready to start cycling automatically. These replacement modules actually arrived a few weeks ago, but I was busy with the code. Priorities. So let's set it all up. And I made it so that I can log on my Raspberry Pi remotely. So earlier I had it connected to a monitor and a separate keyboard, but now I'm using my desktop computer to access it through Wi-Fi. And yeah, I can access it through my phone from anywhere too.
Okay, here goes the first one. And the second one. You can't see anything, but you can hear it.
So here are the 2 different Pis. Looking at them remotely. And now we wait. So I'm at work right now, but let me whip out my phone and see how it's doing. Okay, you're good, keep going. Well, after a few days, we're done. I got the spreadsheet from my Raspberry Pis and everything looks good, so now it's time to balance the pack again. Alright, the pack is back in the car, and while I test it, I'm gonna cycle my friend's pack. Ah, this is so much easier now that it does it by itself. Okay, let's take my car for a test drive. My favorite part. And wow, look at that! If I drive conservatively, I can get some pretty juicy miles per gallon. Alright, let's go home. Wow, what a nice surprise. I did not expect to come home to this. Thank you, wifey. This project took way too long. And there's my friend's pack still being cycled. And here we are a year later, still running strong. My normal driving is quite obviously not that conservative. And I like to blast my air conditioner, which takes a massive toll on your MPG. But the engine has not been staying on for long periods of time like it used to, and it has not been revving up really loud either. If you like this video and you learned something, please consider supporting me on Patreon. I just set it up for the first time ever, so this is totally new to me. All your support will go toward making more videos, and I have a lot of fun project ideas for upcoming videos. One of them has to do with one of my favorite video games. And if you're unable to support me on Patreon, you can still support me by giving this video a thumbs up and subscribing to my channel. Thanks again for watching, and I'll see you next time.